Hello, and welcome to the second part of the Advanced Synthetic Aperture Radar webinar series. This is Erica Podest, and I will be your lecturer for today's webinar, which will focus on the use of SAR for flood mapping. The structure of today's webinar is the same as the previous one, where I will cover SAR theory as related to flooding, and I will then go through a demo on how to generate a flood product. The next webinar series will be on crop mapping by Dr. Heather McNairn from Agriculture and Agri-Food Canada on August 14th, and the last webinar will be on interferometric SAR for assessing surface deformation from earthquakes by Dr. Eric Fielding from JPL on August 16th. Each webinar will be done in both Spanish and English. The Spanish webinars will all be at 1400 UTC, and the English ones will be at 2200 UTC on the same day. Remember, you will be able to access the presentation material and the recordings online in a couple of days. So the learning objectives. I expect that by the end of today's webinar, you will be able to understand the advantages of SAR over optical systems for flood mapping, as well as what you can and cannot do with SAR versus optical. You'll understand the information content in SAR images and its limitations for flood mapping. You'll also understand the optimal SAR sensor parameters for flood mapping. And finally, through the demonstration, you will learn how to generate a flood map using SAR data. First, I want to make sure that we're all on the same page about what I mean when I say flooding, since the terminology can vary. In this case, I'm referring to the occurrence of a water surface beneath a vegetation canopy, regardless of whether it is related to forests or agriculture. When I refer to an inundated forest, it means that underneath the vegetation canopy, there is water above the soil surface. In agricultural or herbaceous areas, the leaves or stems of the plants visibly emerge above the water surface. We can also detect flooding where there is no standing vegetation, and I will call this open water. The type of flooding that I will cover can be caused by natural processes such as the seasonal flooding of wetland ecosystems, or by human-driven flooding such as flooded rice fields, or flooding caused as a result of a natural hazard, such as, for example, hurricanes or extreme precipitation events. For natural systems, these types of products can help reduce uncertainties in the spatial and seasonal extent of methane sources and sinks associated with wetland ecosystems, or the cultivation of crops that require standing water, such as rice. Also, these type of products can help monitor inundation extent and dynamics for disaster assessment and management. So radar versus optical. Radar really does offer a unique advantage to mapping flooding versus optical because of two reasons. The first is that radar can make observations of the surface of the Earth regardless of day or night conditions or almost any type of weather condition. Optical, on the other hand, is hindered by darkness and by clouds, making radar especially useful for studies of the tropics or to assess areas where a flood-related disaster is occurring or has occurred, because such disasters are characterized by heavy cloud cover. The other main advantage of SAR over optical is the ability to detect flooded vegetation, given the radar's capability to penetrate through the vegetation canopy, and this is wavelength dependent, and its sensitivity to standing water underneath the vegetation. Optical only sees the top of the canopy, unless there are large gaps. The advantage of optical has really been high temporal repeat and spatial resolution throughout a long time period. However, that has started to change with operational radar data such as Sentinel-1, and it will change even more in the future with upcoming satellites such as NISAR, SWAT, SAOCOM, and Biomass. So SAR signal scattering over inundated regions. Here I will briefly review the radar backscattering mechanisms in general, with an emphasis on the ones that are primarily relevant to flooded vegetation and open water, shown in red boxes in this figure. So this figure illustrates the different backscattering mechanisms, starting with the one on the far left, which is specular scattering, which occurs when there is a smooth surface, such as a calm water surface, and the signal scatters away from the satellite. This results in open water appearing as dark in the image. The next one is rough scattering, which results when there is slight roughness on the surface, causing the signal to scatter in different directions, but mostly away from the satellite. An example of this would be a water surface that has some level of roughness caused by either short floating vegetation, wind, or heavy rain. Such an area could appear dark, but not as dark as a water surface that is completely smooth. As the surface gets rougher, as shown in the next figure, the larger the signal scattered back to the satellite, and the brighter that pixel will appear on the image. The next signal interaction is volume scattering, which occurs when the signal is scattered multiple times and in multiple directions within a volume or medium. In the case of vegetation, the signal can scatter from multiple components, such as branches, stems, leaves, trunks, or soil. The final backscatter mechanism is called double bounce, which is the one on the far right. And it results when two smooth surfaces create a right angle that deflect the incoming radar signal off both surfaces, causing most of the energy to be returned to the sensor. These areas appear very bright in the image and are commonly seen in flooded vegetation because of the interaction between the smooth water surface and vertical structure of the vegetation, such as the trunks. Double bounce is also characteristic of urban areas because, again, we have a smooth surface, which is, say, for example, a road, and then we have vertical structures such as buildings. So you have the same backscattering mechanism, and these areas appear very bright. So this slide shows SAR signal scattering over inundated regions, and this figure is an L-band HH polarized image from the Japanese pulsar sensor on board the ALO satellite over an area near Manaus, Brazil. It is a great example showing flooded vegetation as well as open water. The river running through the middle is dark because open water is a smooth surface and causes specular scattering. The very bright white areas throughout the image are flooded vegetation. And what is really impressive is that in some areas, even though you cannot see specular scattering from the river because it is either too small or it is covered by vegetation, however, you can still see the river's extent through flooded vegetation because the signal is penetrating through the canopy and double bounce is occurring. This level of detail on flooded vegetation is truly unique to radar. So let's start out by discussing the SAR signal response to flooded vegetation as a function of wavelength. Generally, the longer the wavelength, the higher the capability of the SAR signal to penetrate through the vegetation canopy all the way to the surface. The table on the right lists commonly used bands in radar and their wavelength range. So SARs operating at X-band are generally operating at a wavelength of around 3 centimeters, at C-band at a wavelength of around 5 centimeters, and at L-band at a wavelength of around 23 to 24 centimeters. As you can notice, this range is quite wide. Numerous studies have concluded that L-band is suited to detect inundation beneath a forested canopy and should be the preferred wavelength for this purpose. However, that capability of L-band and also of other bands to penetrate some forested areas can be reduced or are even non-existent depending on the gaps in the canopy, or especially on the vegetation density. As an example, a couple of years ago, we were conducting some wetland studies in the Peruvian Amazon, and we overflew UAVSAR, which is a JPL L-band airborne sensor, over our site of interest, while at the same time, we had someone on the ground collecting site data. This person was in water up to his knees. However, the radar data did not see any flooded vegetation because the vegetation was simply too dense and the signal could not penetrate all the way down through the canopy. In comparison to L-band, the ability of shorter wavelengths like C-band or X-band to penetrate the vegetation canopy is reduced. Although the penetration of C-band is limited in comparison to L-band, studies have shown an increase in C-band backscatter for flooded vegetation during leaf-on conditions and especially during leaf-off conditions because you have more gaps in the canopy. So C-band generally is more useful at the initial growth stages and if the density of the vegetation is low. Also, C-band data is more sensitive for detecting paddy rice cultivation and herbaceous wetlands. X-band sensors, so for example AIRSAR X, in general have even more limited penetration through dense vegetation as a result of high interference with leaves, where backscatter is dominated by volume scattering. However, there have been some studies that have shown the potential of X-band to identify flooded vegetation for sparse vegetation or during leaf-off conditions. In this case, the transmittivity of the signal through the canopy is increased due to gaps in the canopy of very low biomass areas and the contribution of double bounce dominating the volume scattering. Some other studies have demonstrated the ability of X-band to map flooded vegetation in flooded marshlands and in olive groves. So in summary, L-band is better suited for dense vegetation, but shorter wavelengths might give you reasonable results, especially if there are many gaps in the vegetation. The shorter the wavelength, or the shorter wavelengths are better suited for lower vegetation in general. This is an example of signal penetration through vegetation to detect flooding. Here we have multi-frequency images at C, L, and P bands obtained from JPL's multi-frequency airborne radar called AIRSAR. The area imaged is a wetland in the Manu National Park in Peru, and this is an image from 1993. Now remember that C-band has a wavelength of around 5 centimeters, L-band around 24 centimeters, and P-band around 40 centimeters. As you would expect, the longer the wavelength, the deeper the penetration through the canopy, and the better you can detect flooded vegetation. So you can clearly see here the bright areas where there is flooding, and note all of the white areas in the P-band image that are either not present or less bright and extensive in the L-band image or the C-band image. In fact, if you take a look at the C-band image, there's hardly any flooded vegetation being picked up. As you know from previous material, backscatter is dependent on two surface parameters, which are structure and dielectric. There are three parameters related to structure: size relative to wavelength, orientation, and density. In radar, the length of the wave or the wavelength will determine its interaction with surface objects. Size relative to wavelength defines the surface roughness. So if wind ripples on the surface of the water are relative to the wavelength, then the surface will appear rough. Remember that the darker the pixel, the smoother the surface in relation to the wavelength. As the surface roughness increases, the backscatter intensity will increase. In the case of open water, as the surface roughness increases, the brighter the pixel. Orientation influences the interaction of the waves that are either horizontally or vertically polarized. Double bounce, which is characteristic of flooded vegetation, occurs when there are two smooth surfaces creating right angles, such as a water surface and a trunk, resulting in most of the radar signal scattering back to the satellite and appearing very, very bright. If the orientation of the trunks are not perpendicular to the water surface, then double bounce will not occur. I will discuss this further along. Finally, the density of the scatterers and the biomass in the case of flooded vegetation will also influence the double bounce signal return. The greater the biomass, the less penetration through the canopy. This is also a function of wavelength, of course. And the greater the density of scatterers, the less the penetration. If there are gaps in the vegetation canopy, there is a larger likelihood for the signal to penetrate all the way through to the surface. Polarization refers to the plane of propagation of the electric field of the signal, which can be in the horizontal plane or in the vertical plane. Irrespective of wavelength, radar signals can be transmitted and or received in different modes of polarization. There can be 4 combinations of both transmit and receive polarizations, which are HH, horizontally transmitted, horizontally received; VV, vertically transmitted, vertically received; HV, horizontally transmitted, vertically received; and VH, vertically transmitted and horizontally received. Penetration depth is influenced by polarization. In forests, HH tends to penetrate deeper into the canopy because it tends to be less attenuated than VV. HV is more sensitive to volume scattering and hence is a good indicator of vegetation cover and biomass. This is an example of multipolarization images from ALO's pulsar over a part of the Pacaya-Sumerian Natural Reserve in Peru, which is a vast wetland ecosystem. The images are at L-band and at HH, HV, and VV polarizations. The very bright areas is where double bounce dominates, and this is where there is inundated vegetation. The very dark areas are open water, and you can clearly see a river through the middle of the image, as well as some open water bodies north and south of the river. Note the difference in backscatter magnitude between the different polarizations. If you focus on inundated vegetation or the areas that are very bright, HH polarization is way more useful for distinguishing flooded from non-flooded vegetation. VV shows flooded vegetation to a lesser extent and even lesser by HV polarization. In general, HH polarization penetrates deeper into the vegetation canopy than VV, and when striking the water surface is more strongly reflected in comparison to VV polarization. HV is more sensitive to volume scattering because of its depolarizing characteristics. Here you can see an RGB image of the different polarizations, HH, HV, and VV. False color images are an ideal way to visualize the information content of the different polarizations through color combinations, because you can see the information content unique to each polarization or for combinations of polarizations. So in this case, this is a false color composite of the same 3 images that you saw in the previous slide. HH is in the red channel, HV is in the green channel, and VV is in the blue channel. The pink areas that are popping out are those areas where flooded vegetation is present. This example shows a pulsar image for an area near Manaus, Brazil, at 3 polarizations, HH, HV, and VV. Note the backscatter intensity of the river that goes through the middle of the image. Open water is a smooth surface which causes specular reflection, resulting in the radar signal being scattered away from the satellite and appearing very dark in the image. Here you can see that open water is much darker at HV than at HH or VV, and hence easier to differentiate. The reason for this is that since water is a smooth surface scatterer, there is no depolarization of the signal. So remember, the signal tends to be depolarized whenever it scatters multiple times. So for example, when you have vegetation, the signal scatters multiple times from the branches, the stems, the trunks, the leaves, the soil. And that's called volume scattering. So depolarization normally occurs whenever you have volume scattering, but not when you have specular scattering. So this is a subset of the same pulsar image shown in the previous slide. It is zoomed over an area where you can see roughness on the surface of the water of the main channel, which is most likely caused by windy conditions. Notice that as you move east and up the tributary, there is smooth water. There's a transition where that water goes from rough, it's a bit higher backscatter, to very low backscatter. That means the characteristics of that water have changed from rough to smooth and more of a specular reflector. And so that's the reason that there's a decrease in backscatter in both the HH and VV polarizations. So the utility of SAR data for detecting flooded vegetation is influenced significantly by the incidence angle. Incidence angle is the angle between the direction of the incident wave and the Earth's surface plane. In radar, the incidence angle increases across the swath from the near to the far range. The area closest to the satellite is the near range, and you will find smaller incidence angles than the area furthest from the satellite, or the far range. Small or low incidence angles will result in greater penetration through the medium and higher backscatter than large incidence angles. Large angles, on the other hand, will be more sensitive to surface roughness and will penetrate less into the medium. For the detection of flooded vegetation, steeper incidence angles are preferred because the signal has a greater penetration through the canopy and reaching the water surface underneath. Large incidence angles will be more sensitive to vegetation structure and less likely to penetrate through the vegetation canopy and detect flooded vegetation. And this is an example of the effect of incidence angle variation. On the left is a Sentinel-1 VV image, and on the right is the incidence angle variation for the same image. So you can see that it goes from 30 to 45 degrees. The radar is right-looking. Note that as we move across the swath from the near to the far range, the image becomes increasingly darker in tone, around a 3 to 5 dB difference in backscatter. If you measure, for example, the same forest at different incidence angles, then the measured backscatter will be different, even if there has been no physical change in the forest. Every surface feature will have a backscatter that is a function of incidence angle. So you need to be careful when comparing backscatter of a feature when there is a large variation in incidence angle. Incidence angle can especially affect the appearance of smooth surface or smooth targets on the image, such as open water. Smooth surfaces can appear brighter than rough surfaces at small incidence angles, and that's usually less than 20 to 25 degrees. Now let's discuss a source of confusion that might lead to errors when classifying open water. This is a pulsar image near Manaus, Brazil, at HH, HV, and VV polarizations. You can see that the water is dark, but north of the river there are areas that either have no vegetation or very low vegetation, and these areas are easily confused with open water. One way to try to clear this up is using image ratios such as HH over HV. Another source of confusion that might lead to errors when classifying flooded vegetation are urban areas. Here we have a pulsar image containing the city of Manaus in Brazil and its surroundings. It clearly shows flooded vegetation, which are the very bright areas around the river. On the top, labeled in red, is the city of Manaus, which has a population of 2.5 million people, including its suburbs. Notice that the city appears very bright as flooded vegetation. This is because the dominating scattering mechanism is double bouts. Right angles form between smooth surfaces such as roads and vertical structures such as buildings, causing this high return in urban areas. One way to at least partly clear up this confusion is through the use of texture measurements. Textures provide information about the statistics of the pixels within a box, and the box size is defined by the user. Some textures, such as energy or entropy, provide information about homogeneity or inhomogeneity of the pixels within the box. In my experience, such measures help separate urban areas from flooded areas because urban areas tend to be more homogeneous in texture than flooded areas. Here's an illustration of urban areas and flooded areas at different polarizations. You can see that at HH, both urban and flooded areas are very discernible. At VV, urban areas are more discernible than flooded vegetation. The reason for this is because the signal is attenuated by vegetation, but not at the same level by urban areas. At HB, urban areas are minimally discernible. Here's an example of flooding that occurred in the city and surroundings of Houston, Texas in the United States. This flooding was caused by a large hurricane called Hurricane Harvey in late August of 2017. These are radar images from the European Space Agency's Sentinel-1 satellite of before, during, and after the event. The images cover an area of approximately 220 by 190 kilometers. The area marked with the red circle is the city of Houston and some of its suburbs. There is no significant change in brightness over the city itself. However, inundation in the surroundings is discernible because ponding of water forms smooth surfaces that create specular scattering, and those areas appear dark. Note some of the water bodies that are present in the middle image, which I have marked with red arrows, that are not present in the far left or far right images. Also note the disappearance of some of these water bodies a couple of days after the event on September 5. This is a false color RGB image of the same area. Here I used two images before and during the event. So channels R, red and blue, contain the during the event image, while channel green contains the before the event image. The areas where there is a predominant color means that the backscatter value for that area was higher in the image containing that color or combination of colors. So for example, anything that is green means that backscatter was higher before the event. Areas that are pink means that the red and blue channel values, which in this case are the same, are higher than the green channel. Therefore, wherever green is higher means that before the event the backscatter was higher than during the event, because the area is now inundated and there is water, or there's a water surface that is causing specular scattering and hence a very dark backscatter return. So the green areas, you can interpret those as areas that are now inundated. There's standing water. The areas that are pink means that they are higher backscatter than before the event. Therefore, that area is either inundated, so there's inundated vegetation, or the soil moisture content of the soil is higher than before the event. Note that the urban area remains high in both images. This is another similar event. Here we have two Sentinel-1 radar images. The false color images are VV, VH, and the ratio of VV to VH for each date. This area is part of the state of South Carolina in the eastern coast of the United States. A large hurricane called Hurricane Matthew caused major flooding in this area on October 2016. The two images are before the event and shortly after the event. Note the orange areas that pop up along the coastline after the event. This indicates that these areas are inundated. In summary, SAR backscatter is not good at assessing flooding directly in urban centers, but can assess flooding in the human-natural interface within or surrounding urban areas. Now let's discuss the geometric distortions due to topography that are commonly found in radar images. Here we have two examples of distortions. They're layover and foreshortening. Layover occurs when the radar beam reaches the top of a tall feature before it reaches the base. As a result, the top of the feature is displaced towards the radar from its true position on the ground and lays over the base of the feature. Layover is most severe for small incidence angles at the near range of a swath and in mountainous terrain. Foreshortening occurs when the radar beam reaches the base of a tall feature tilted towards the radar, such as a mountain, before it reaches the top. Because the radar measures distance in slant range, the slope, A to B, will appear compressed and the length of the slope will be represented incorrectly. So depending on the angle of the hillside or mountain slope in relation to the incidence angle of the radar beam, the severity of foreshortening will vary. These distortions can complicate SAR-derived flooded classification. In severe cases, the layover and shadowing produced by mountainous terrain makes classification inappropriate. In less severe cases, ancillary digital elevation data can be used to generate approximate corrections for terrain effects prior to classification. The final effect that topography can have on the signal is shadowing, which occurs when the radar beam is not able to illuminate the ground surface. Shadows occur behind vertical features or slopes with steep sides. Since the radar beam does not illuminate the surface, shadowed regions will appear dark on an image because no energy is available to be backscattered. As incidence angle increases from near to far range, so will shadow effects as the radar beam looks more and more obliquely at the surface. These shadows can be easily confused with open water when mapping inundation. There are ways to correct for shadows through interpolation. However, I personally prefer to leave the shadow areas as areas of data gaps rather than use interpolated values. One final thing to consider when doing a flood map classification is speckle, which is that salt and pepper appearance of radar images. In order to reduce the effect of speckle, you need to apply a filter, which will reduce the resolution of your image. Therefore, keep in mind that with radar, images might be at a given resolution, such as 10 meter. However, after applying a filter on an individual image, the spatial resolution of that image will be lower. The last example I want to show you is that of radiometric distortion over areas of topography, especially complex topography. Wherever you have slopes facing the satellite, you will get a bright return, sometimes bright enough to be confused with flooded areas. This example shows such an area in the Andes from a Sentinel-1 radar image. You can partly correct for this by performing a radiometric correction to your data, and this is something that is part of the processing sequence of radar images when using the Sentinel Toolbox software. SAR datasets have improved significantly in the last couple of years, and this list shows the legacy, current, and future SAR datasets. The ones with the green box indicate that the data are freely available, which you can access through either the Alaska Satellite Facility or the European Space Agency's Copernicus Hub. Note that the legacy datasets start with CSAT in 1978, which was an L-band sensor that flew for only a couple of months. During the 1990s, there was JRS-1 and ERS-1 and 2 going into the 2000s with ENVISAT, ALOS-1, and RADARSAT-1. Currently, there are a number of SAR satellites in orbit with Tandem-X, which is an X-band radar satellite from the German Aerospace Center, RADARSAT-2, which is C-band from the Canadian Space Agency, Cosmos SkyMed, which is an Italian X-band SAR, Sentinel-1, which is a European Space Agency SAR operating in C-band, and finally PASSAR, which is a Spanish SAR operating at X-band. There are future satellites coming up with SALCOM, which is an Argentinian SAR which will operate at L-band. And there is also the RADARSAT constellation, which will operate at C-band. NISAR is a NASA Indian Space Agency L-band and S-band sensor to be launched in 2021. And Biomass is a European Space Agency P-band sensor also to be launched in 2021. So it's very exciting times ahead for those people that are using radar in their research and applications. And this chart shows current and future satellites grouped according to bands, and the far right indicates their repeat cycle. Note that they have repeat cycles of just a few days, which allows for a constant monitoring capability. I want to briefly touch on NISAR, which is a NASA and Indian Space Agency satellite that will launch in 2021 and will operate at L and S bands. It will have 3 to 10 meter resolution depending on its mode of operation. And it will provide repeated observations which will allow for applications such as ecosystem, hazard, and disaster monitoring that include ecosystem disturbances, ice sheet collapse, and natural hazards such as earthquakes, volcanoes, and landslides. So next, I will show you a demo on flood mapping using the Sentinel-1 toolbox. Welcome to the second part. The demo that we're going to do is going to consist of looking at flood extent due to a hurricane. And the area that we're going to focus is the east coast of the United States, a state called South Carolina. There was a hurricane that hit this state back in 2016, in October of 2016, and it caused vast inundation. So we'll be looking at images from before the event and after the event. And the images that we'll be using today are images from the Sentinel-1 satellite. This is a satellite that operates at C-band, and we'll be using two polarizations, VV and VH. And this satellite is from the European Space Agency. The data is freely available, and you can access the data through the Alaska Satellite Facility. And so I'll walk you through how to access this data. Just do a Google search for the Alaska Satellite Facility. And by the way, you can also access the data through the European Space Agency's Copernicus search engine. And the only difference between the two is that there is a bit of a delay with the data that's placed in the Alaska Satellite Facility server. There's about, like the most recent one is probably from 3 days ago, while the ones that are placed at the European Space Agency's search engine are, I think, from the last day. So if you're looking for images to do like a disaster assessment, something that's very recent, then that's the best place to go. But today's demo, I will be using the Alaska Satellite Facility. And so one thing to mention is, you noticed I mentioned the polarization, right? VV and VH. And in the presentation, I talked about the different polarizations, and I talked about how HH is really better suited for looking at inundation because it penetrates further through the vegetation. And so the reason we're using Sentinel today is to give you a sense of using a different data set from the last demo that we did. So the last one we used Delos Pulsar. Today we're using Sentinel, and the area where we'll be focusing does not have dense vegetation. It has relatively short vegetation. There's some mangroves and grasslands along the coast. And so VV is actually acceptable. It works well, and you can see the inundated vegetation. So let's get started. Once you get to the main page of the Alaska Satellite Facility, go to Datasets and click on Sentinel-1, and it will take you to a page that provides more information about the dataset, documents and tools, and the data. But let's go straight to do our search. So click on Find Sentinel-1 Data, and it will pop a window asking you what sort of search you'll want to do. Gives you three options. Select the first one, the geographic search. And down here, this is a tutorial. It steps you through how to do the search, but I will step you through that, so I'll just dismiss that box. And the area that we're interested in, I'll just zoom in, is here. So this is actually the city of Charleston in South Carolina, and I will draw my box here around this area. So this was actually in one of the examples I showed in the slides, these images. So we'll look here on the left, and we've defined the geographic region. The date, as I mentioned, this event occurred in October of 2016. Actually, the hurricane made landfall in this area on October 8th of 2016. So let's go up to 2016, select October, and do a search starting from the 1st of October through let's go through the 18th, okay? And then down here, data set, the default is Sentinel-1A and 1B, leave it like that, and then just press search. Okay, and then on the right pops a list of all of the images that somehow overlap our area of interest. And the two images that I have selected are, let's zoom out here a little bit, are this one. So it's from October 16th. So this is after the event. Sentinel-1 has different modes of operation. This one specifically is called interferometric wide swath mode, and it's the one most commonly used for land cover applications. And it's a VV-VH polarization, and this is an ascending node. This is very important. I'll reiterate what I mentioned last time, is to never mix paths. So never mix your images, ascending and descending, never do that. If you're doing a multi-temporal analysis, treat the ascending images in one pile and do the analysis with those, and do the analysis with the descending images in a different pile. The reason for this is because the viewing geometry is different. Okay, so here we have a number of different images, and the one you'll want is the one projected on the ground range. So you want the GRD image, this one. All right, so you click download, and all you need to do to download the data is register into, on the system, on the Alaska Satellite Facility system, and then you can download them for free. So I've downloaded this one already, and let's go down the list to select the next one. So the next one before the event. Remember, the satellite reached land on the 8th of October. And so the one before the event that I selected was this one down here. And this is from the 4th of October. Okay, and just from taking a look, you can see that these areas around the coastline don't pop up as in the other one. So that's all inundated vegetation. We'll take a closer look at all of that. Okay, again, interferometric wide swath, ascending, very important, polarization BVVH, C-band, and so again, we'll download the GRD image. Okay, so that takes care of accessing and downloading the data. And now let's go ahead and open our toolbox. Actually, I'll close this. And our snap toolbox, and let's open the images. So what I'll do here is, since these images are pretty big, what I'll do is I won't go through the actual processing. I'll show you how to do the processing of the data, but this is going to be like one of those cooking shows on TV where they show you how to do things, and then they put it in the oven, and out comes the baked product. Okay, so that's what I'm going to do. So let's start out with the data sets, the raw data, okay? So you don't need to unzip the files that you downloaded. The Sentinel toolbox recognizes the file and it unzips it. Okay, so in order to open the file, you just select, so let's see, you select the zipped file. So we select these two files. These are the ones I downloaded. So October 16th and October 4th, just a zip file, and it'll open it. Okay, so I've got it opened here, and this is the one from October 16th, and let's just take a look at the images, make sure they look okay, and this is always good practice, just in case there's some issue with the image. Sometimes there's banding introduced during the processing of the image, or there's some issue with the image. So it's better to catch those things at the beginning before you run. You spend a lot of time just running things on it and realizing after an hour of doing the processing that there's an issue. Okay, so there you go. So each image has a VH and VV band. Okay. That's the VV from 2016, and this is the VV from 2004. Interesting. Look at the water here. All right. So there are a series of steps that you need to take to process the data. With ALOS Pulsar, you did not do that because the data was already radiometrically terrain corrected. And so the data that we downloaded in the first demo on Tuesday was just pretty much ready to go. Other than applying a filter, it was ready to go. Here, we need to apply the processing steps. And these are, you do a radiometric correction, you apply a speckle filter, you terrain correct the image, and then you're ready to start manipulating the image, okay? So at that point, you can then export your image into your software of choice, whatever you're using, QGIS, ArcGIS, whatever. And Snap actually is really great about being able to export files into different formats. So you got file, and you've got here an export button. And it's got all of these different formats, NetCDF, GeoTIFF, HDF5, ENVI, if that's what you use, and other, you've got a number of different options here to export the file. And you can even also export for visualization onto Google Earth. And we'll do that actually at the end. Okay, so the images are open. The first thing we do, and I'll close this to just keep my box here uncluttered. So I'll close, actually, after I apply the first part of the process, I'll close them. So the first thing we do is we apply a radiometric calibration. To do that, you go to Radar, Radiometric, and you select Calibrate. Okay, and you select, we need to apply this on each of the bands. So we start with band 1, which is the one from the 16th of October. So the Sentinel software tags on to the file name a description of the process that it's applying. So here it's tagging on CAL, so you can recognize and know that this file has been calibrated. And down here, you define the directory where you want your file to go. Processing parameters, you don't change anything. You want the calibration on both polarizations, and you want the output as sigma naught band. Okay, so you press run, and once that's ready, that'll be file 3, and then you rerun this with the second file, which is the one from October 4th, and exactly the same thing, and you'll have a file that will be file number 4. Okay, so now I will close these. So now I'll close the original files. And let's take a look at the radiometrically corrected files. So we have sigma naught, VH, and VV for October 4th. And down here, we've got sigma naught VH and VV for October 16th. Looks good so far. All right, the next step is applying a filter. So you're all familiar now with the issue of radar images that they have this, they've got speckle. So it's a salt and pepper effect, and that salt and pepper effect can just propagate to your classification results. So we want to try to clean that up a little bit. And the way we do that is we go to Radar, we select speckle filtering, single product speckle filter, and same thing here. You select the input file, and the input file that we want to select is the calibrated, and output file name, it tags on SPK, and then processing parameters. Okay, we want both polarizations. And then here, there's a whole list of different filters that you can explore. One of the more common ones is actually the Lee filter. And I've used a 7x7 window. How do you determine the optimal window? It just totally depends. It depends on how speckly your original data is, how much resolution you're willing to forego, I guess. Yeah, that's a word to use. So the larger the box, the more resolution you lose, right? So this data is 10 meters in resolution. And so we apply a filter that has a box of 7 by 7. The actual resolution is going to be 70 meters. So the way this filter works is that even though you apply a 7 by 7 box, the result, that SPK image, will have the same size as the original image. So it's actually gridded to a 10-meter resolution, but the actual resolution is 70 meters. Okay, so you run that, and then you do the same thing for the second file. And the results are here. And actually, let's open that. And I'll open 2 files side by side so you can see the difference between the filtered and the non-filtered file. And so one thing to keep in mind about radar is that it's a little deceiving when you talk about radar resolution. Like someone might say, yeah, okay, that radar data is 10 meters, but actually you'll always have to, or pretty much most of the time, you'll have to apply a filter, a speckle filter, to the radar data. So assume that whatever product you're generating from radar data is not going to be at that original resolution. It's going to be at some degraded resolution. Okay, so that is something really to keep in mind with radar. With optical, I know it's not like that. With optical, if your image is 30 meters, then you're generating a 30-meter product. Okay, so let's tile these images side by side. Okay, so this is, so here we have October 4th, the VV filtered, and I will load October 4th VV unfiltered. And we can put them side by side. So to see these images side by side, you go to Window, and you do a tile horizontally. And let's go here. And you can zoom in, and you see the difference between the filtered and the non-filtered image. Okay, makes a big difference. Big difference. Okay. All right. So the next step is, oh, and one thing I wanted to show you before I go to the next step is, if you want information about your file, then you click on the file name and you go to Analysis and you click on Information. And it will tell you, it will give you some basic information about the file, especially the if you want to know the size of the file. So look at the size of this file. It's 25,321 pixels by 16,733 pixels. So it's a very large file. And in the next step, we'll be reducing the size of this file so it becomes more manageable. And you'll want to do this too, especially if your computer is not very powerful or you'll want to subset the image. So what I suggest is, when you start playing around with this and just exploring how to use it, just cut a subset so you don't have to wait through these processes to run. It will be much quicker, and it's a much less frustrating way to become familiar with the software rather than having these crashes or having to wait a long time. Okay, so the next step is we apply the geometric correction on the image. And we go to Radar, select Geometric, select Terrain Correction, Range Doppler Terrain Correction. Okay, and we select the speckled the filtered image. Okay, and here, what the software does is it uses a digital elevation model to do the terrain correction, and it automatically downloads the DM. Okay, and if you click here, you have a list of different DMs that it can automatically download, or you can also specify your own DEM. But let's just keep the default, which is SRTM. And then the source pixel, so the output will have 10, the original image is 10 meters, and it's saying, okay, the output will be 10 meters, but we want to reduce the size. So let's just make it 70 meters. Since the actual resolution is 70 meters, let's just make the size to match the actual resolution. Okay. And then one thing that's important is to deselect, mask out areas without elevation, because what that will do is it'll mask out like the ocean, for example, and it's just going to look funky here at the coast. Okay, and so you hit run, and then you do the same thing for the filtered image number 2. Okay, so I'm going to do close. Actually, I'm going to close some of these files. Okay. So the terrain corrected image is this one. And you probably noticed something very striking. And since I cannot hear you, I will assume that what you're noticing that's striking is the orientation of the image, which is completely correct. You guys are correct. So the reason for this is because the original image is in the satellite orientation. And once you terrain correct the image, it's in the correct orientation, as it should be. So if you want to look at the coverage of the image, you can always go to the world view and look at the coverage of your images, okay, and how they should look, and they look to have the correct orientation. All right. So what we'll do is we will, with radar, and when you're working with radar and with publications, the way to represent backscatter values is dB. That would be decibels. So it's a power unit that's nonlinear, right? And so you're going from a linear value, sigma naught is linear, to decibels, which is nonlinear. The way to do that is you do 10 log of the value of the pixels in sigma naught. Okay. Now it's already a function here in the Sentinel toolbox. So it's you click on the file name and you do linear to from dB, and it says, do you want to save it as do you want to convert it to a virtual band? And you say yes, and then you do the same thing for the second one, and you say yes. Now virtual band means it saves it in memory, so we actually want to have it as part of the file, and so you go to you go to the file and you convert band. So now it's part of the file. It's not in memory, and you go and you save the product, okay, just to make sure everything is saved. So you have these 4 files now under this file name. And you do the same thing with the second one. Okay, and you convert the band, And now let's just take a look at, do an RGB just to see visually how some of these images look. So let's do an RGB of the 2016 image, and let's do it with dB. So let's do VV. I always try to put VH in the green channel just because the cross-pol polarization is so sensitive to vegetation. It pops up in the green channel. And then we'll do VV here. And we'll stretch. We need to stretch the histogram. It's always nice to look at the histogram to see how your values are distributed, right? So we put VV in the red channel and take a look at these two peaks. This peak down here, that's water, and this peak here, that's everything else. Okay, so let's just play around with the histogram to make this look a little better. This is VH. Also, you've got two very distinctive peaks. And then this is the same one. So we've got VV. Okay. So what's happening here? What are you seeing? So remember, the colors that you're seeing, the predominant colors, means that whatever you put in that channel, whichever band you put in that channel, that value is higher, right? And that's why it's predominantly that color. And so everything that's predominantly green, that means that whatever you put in the green channel, in this case we put HV in the green channel, is higher than VV. Whatever you see in pink, so pink is the combination of two colors, right? So it's a combination of red and blue. So that means that whatever you see as pink is a combination of what's in the red channel and in the blue channel. And that's what you would expect, because we have the same band in the red channel as in the blue channel. We have VV in the red channel and we have VV in the blue channel. So it means that in VV, these areas are very bright. So you get double bounce, and this is some sort of flooded vegetation. And in the VH, you're not getting that double bounce. So remember, VH is sensitive. It depolarizes in areas where you have a vegetation, but wherever you have flooded vegetation, it really doesn't penetrate, especially dense flooded vegetation. It doesn't penetrate, or it's least likely to penetrate to the ground and detect that flood state. So that's why in VH, these areas are dark, and in VV, they're bright. They're just popping out. Okay? And so we see all along here, these pink areas are areas where it's brighter in the VV than in the VH. And these are probably fields that are either flooded or they're wet. They're wetter. So remember, when the dielectric property increases, there's more reflectivity. And that might be what we're seeing here. All right. And then the dark is open water. All right, so let's carry on, and let's do an RGB quickly here of the one for October 4th. Open RGB, and we'll do the same band combination. Now, this band combinations in radar, it's not like optical. It's more of, you just need to play around and find the optimal band combinations. More than anything, you need to understand color combinations, right? And the information content that is popping up when you do these false color composites based on the different colors, right? So if something is green, that means that whatever's in the green channel is brighter than whatever's on the other two channels. If something is pink, it's a combination of blue and red. If something is yellow, it's a combination of red and green. So that's the best way to interpret these false color composites. Okay, so let's open this one. And again, and this is interesting. So this is the one from October 4th, and same combination, BV, BH, BV. Interesting here, take a look at this histogram. It doesn't have that double peak. It just has one. And so the reason for that is because the water is quite rough. It was probably a windy day, and so there's quite a bit of roughness here in the ocean. And so you don't have those really low values over water as you have here, for example. So here in the VH, you do have the distinctive two peaks, one water, one land. And then red is the same, we have VV. So let's just... Okay. So more or less, there you go. And you can just from the two RGB images that we've created, you can see differences right away, especially around this coastal area. So there is some vegetation. I think they're mangroves or grasses around the coastline, and you can see that is evident here. But certainly it's not as bright pink. It's not as the area is not as vastly inundated as it is after the event. Okay, so you will have a better sense when we then put both of these together. All right, so the next thing we need to do is, in order to run a classification with the Sentinel toolbox, it needs to have the images that you're going to run the classification on in one file. So we need to stack these files. And the way to do that is you go to Radar, then you go to Co-Registration, and you go down to Stack Tools and say Create Stack. Okay, so you press the Add button, and up pop all of the files that you have open in your window. And you need to deselect the files that you do not want to stack. So let's just remove the files that we do not want to stack. And so you select them and you say minus to remove them. And then you go to the next window, and you need to change one parameter here. It's called Initial Offset Method. Change that from orbit to product geolocation. And then in the right, just the new name will have the stack tagged on, and you run. Okay, so you run it, and the new file name. So the new file name is called stack. So I'm just going to remove these. No. Okay. Now. Okay, so here are my bands. We have 8 files in here. So we have VV and VH for each file, and we have them in dB as well for each file. So let's just focus on the dB ones. There we go. Everything looks good. And those bright points that you see, you shouldn't be seeing those. Those are actually the training areas that I selected. I'll show you that in a little bit. Okay, so what we'll do now is we'll create an RGB of both files. So open RGB image window, and what we'll do is we will put the image, the VV image after the event in the red channel. We'll put the VH dB image after the event in the green channel, and we'll put let's put the VH image before the event in the blue channel. Okay, so one thing we want to look at here is, or detect, is not only flooded vegetation, but we also want to detect open water surfaces. And this will pop up here. I will show you. So let's first stretch this histogram to see things a little better. Okay. Ah, beautiful. Okay. So what we do is we'll zoom in and we'll just look around. And so these areas around here are inundated vegetation along the coast. All of this inundated vegetation. The white areas, remember you have double bounce in urban areas, so these white points, that's urban, that's infrastructure. Okay. And the dark areas means it's dark in all three images. Now the blue areas, remember we put the before image in the blue channel. So that means the blue channel is higher and whatever's in the green and the red is lower. And so that means that the reason things are lower after the event is because there is water in the surface. There's open water here that wasn't there in the image before the event. Okay, so all of these blue areas means there's open water. That's new, that's non-permanent. Okay, so the black areas, that's permanent open water. The blue areas is non-permanent. I'll call that non-permanent open water. Look at the channels here. These are river channels. You can't actually see the river, but they are channels. And I know some of you are interested in detecting like channels. And I'll show you how to train these in a classifier. Okay, so what else? Oh, here we see in these areas, we see these agricultural plots where it's very red. That means it's brighter in whatever's in the red channel. And they're probably red. These fields are probably red because they're wetter, not necessarily because they're inundated, but their soil moisture is much higher than before the inundation occurred. Okay. So remember, this is about 7 days after the event, and some of the water has receded by then. All right. So all of these black dots, that's all open water, permanent open water. And so the next thing we want to do is train our classifier. Okay, so what we'll do is we need to define the classes. And I have defined a number of different classes that are representative of the land cover in the image. And so I'll walk you through the process. So in order to define a class, you go to vector and you say new vector data. And we'll call the first class flooded vegetation. Okay. And then you go in here and all of the areas that are just very bright pink. So you select the polygon tool or the rectangle tool, and you draw a rectangle. So we'll call it. So you'll define that as a. Okay, so that's how you define a class. And you want to make sure that you select enough pixels to fully characterize your class. So make sure your class is not characterized by 10 pixels, right? You want a good distribution of the pixel values that represent your class. And so let's then, so pick a number of classes, and I did this already. So these boxes that you see, those are the classes that I've selected to train my inundation class. Okay, all of these here. And the next class I defined was, so once you're done with that, then you say, okay, well, the next class is, and I'll call this water 2 because I have my classes already loaded up, so I don't want to confuse the names. So I'll call this water 2, and I will draw water 2, and I will draw my rectangle over an area that's representative of water. Actually, this is permanent water. And so you want to select pixels that are representative of water along your image. So I select it here, and I select it in different places. Okay, so the next class I selected was non-permanent water. And that class is here. So the areas that are blue, we said those are open water bodies that were not there in the image before the event. And so those are these blue areas here. Okay, so these are all the rectangles defining my non-permanent water class. Then I picked another class called irrigated fields or saturated fields, and those are these red fields. Okay, and so there's one, and so I just drew a rectangle over some of those red areas. There's another one. All right, the next one I chose is river channels. I mean, you can distinctively see these channels. So I thought, all right, I'll try to classify those. And here's one. So I selected a couple. Here's another one across the image that would represent the variety in values that are found in those channels. Here's another one. Here's another one. And then I selected urban areas, since those have very distinctive backscatter, double bounce. And you can't see it very well here, but this green rectangle, those are my urban areas here, here, here. And then finally, the last class I selected, or I defined, was vegetation. And so vegetation is anything that is green or has some darker tone in green. So I selected a couple of rectangles, or I defined a couple of rectangles along the image here, here, and a couple more in other parts of the image. So overall, I mean, obviously, your classification is going to be as good as you train it. So keep that in mind. And if you're not happy with your classification, it's always good to go back and try to refine your classes. See what's the source of confusion, and then try to refine your classes. All right, so once we have all of the classes trained, then you go into raster and you select classification. And there are two options here, unsupervised and supervised. And I chose supervised. That usually gives you better results than the unsupervised. So of all of these, I chose random forest classifier. I've had a lot of comments about the results using other classifiers, and you can actually just run your classification, all of these classifiers, and compare it. But of all of these, actually random forest is one of the most commonly used classifiers, and it yields very good results. And one of the reasons for that is with other, like maximum likelihood, for example, if you use several information layers, like several images, you've got two different dates, HH, HV, and you might use other layers of information like a DEM. And so the more information layers you use, some can add confusion. So not all of them equally can identify each class, right? So some information layers might be really good at identifying one class, but not so good at identifying other class. So some are a source of noise, basically, to identify certain classes. And so random forest, actually, it doesn't really matter how many input layers you have in your file. It deals with that by just creating many different decision trees and voting on what are these decision trees telling you which class should the pixel be classified as. So it's overall it's much, I think it's a much more robust way of running a classifier. Okay, so having said that, let's go ahead and run the classification. Well, I'm not going to run it, but I'll show you how to run it. So you click plus to define the file that you want to classify. And the one that we want is the stacked one. So we don't want these. So we want the stacked file, and then you go to the next window, and these are the classes that I defined, actually. So it's up to here. Here, these other two were the examples I showed you. And then down here are the files that we want to use to generate this classification. And so we'll use the DB files. And then here, it's just specifying the file name. So it tacks on RF for random forest and the output directory. And so you run it, and the results are here. You get a new file that has RF. I called it RF3 actually. And the results, this is the classification result. Now the colors are not really representative of the colors of the actual classes. So let's just go and change the color table. So you go to color manipulation down here, and you select for flooded vegetation, let's make those pink. For inundated fields or saturated fields, we'll make those red. For non-permanent water, we'll make that black. For permanent water, we'll make that blue. The river channels, we'll keep those as dark green. Urban areas, let's make those white, and then vegetation green. And there you go. That's our classification. And now let's just do a side-by-side comparison to okay. So we do a tile horizontally, and note the nice thing about the classifier is it just classifies the areas where there's coverage in the same coverage in both images. So these areas, these overlapping areas here, are not included in the classification. Okay, so let's go and let's just pan around, take a look at some of these results. So, okay, so the areas along the coastline where you have flooded vegetation is picked up nicely, actually rather nicely. The open water is great, that's very easy to identify. The areas where there was non-permanent water, so the inundated areas that had open water, are the ones in blue. So we're picking those up. what I called the fields. We're picking a lot of those up, but they are prevalent in the image. The channels are picked up, the river channels. So it is very noisy. It's not perfect. There is some noise. And so what we can do is apply a filter to try to clean some of that noise out. And so we'll just select the file name, and then I'll apply the filter. And what we'll do is we'll apply a median 3x3 filter. And okay, so this is our median. And we need to set the colors. So okay, so flooded vegetation. Cyan is so actually okay, there. So I had the color palette saved. And let's compare this with the previous one. Okay, let's do horizontally. And you see it makes for a cleaner, overall a cleaner classification. Now, since you're looking at flooding, you can also clump the classes. And you can merge, so say for example, you can merge those river channels. You can just say that's green. Okay, I apologize. For some reason, it's not taking the colors that I'm assigning to it. All right, but you can merge the classes. Okay, so if you just want to have, like, for example, these flooded areas, then you can make everything else green and just keep the red, keep the blue, well, that's permanent water, keep the black, and then keep the pink. And one last thing that you can do is you can export this and overlay it on Google Earth. So you can export the whole thing as a geotiff too. But here you go to the image, you right click and up pops a window, and you select export view as KMC, and that's it. You just press save, and here's how it looks like. So here I have merged the classes and I've overlaid it on Google Earth. And so if I there you go. So there. All right, so that marks the end of this demo, and I am now open to your questions. Thank you very much for your attention. Okay. All right, so let's start with the first question. Are there any recommended reading or online books that may improve our knowledge about radar and references? Actually, there are, and what I'll do is by the end of this training or on the ARSET website, I'll be sure to include some references. There are other tutorials and there are data recipes. So actually, the Alaska Satellite Facility, where you download the data, if you go to tutorials, they have data recipes, and they walk you through through steps on how to do different things, anywhere from geocoding an image to creating a digital elevation model, interferometric stuff, how to mosaic two images. It's a really great resource. And I can point you to other references as well. The European Space Agency recently had a SAR training, and they had some demos, and a lot of those demos are online. So that training is called Echoes in Space. Okay, so does the soil particle size affect the backscattering? Loam, silt, and clay soils? It will. The texture of the soil has an influence, but really, more than anything, it has an influence on what has the greatest influence is the roughness of the soil and the amount of water in the soil. And so the next webinar, the one on August 14th, will cover not only crop mapping, but how to characterize soil. And Dr. Heather McNair will show an example on how to calculate soil moisture. Is there any useful usage of incidence angle? Do we use them by any means? Actually, more than anything, what you should keep in mind about incidence angle is if it's too large, then you need to be careful, because your same class can look different if it's at the one edge of the image in the near range and in the far range. And so what you want to do is you want to classify that class, and I would call it like forest in the near range and forest in the far range, just to make sure that you can classify it properly. I wonder if SAR could be used to study sudden flash flood in desert areas. It could be. The problem is that it doesn't have the temporal repeat that you would want to monitor a flash flood. So for example, Sentinel-1 is an operational satellite, which data is freely available. And each satellite, so there are two identical satellites, Sentinel-1A and Sentinel-1B. And each satellite has a 12-day repeat pass. So between the two of them, it's every 6 days. And flash floods tend to be very, very quick events. Have you had the chance to have worked on finding the optimal decision lines at H-alpha decomposition for dual pole VV and VH Sentinel-1? I'm sorry, I have not had the chance to find the optimal decision lines in the H-alpha decomposition. Usually when you have two polarizations, it's best to just work with image ratios. And when you have 4 polarizations, that's where decompositions are really very helpful. What are your thoughts on available and new, if any, parameters for dual pole data? Let's see. Your thoughts on available and new for dual pole data. I'm not sure what you mean by parameters. Like, you mean things that we can derive from the data or ratios? So what comes to mind is trying out ratios or applying textures. I talked about textures in the last demo. So the Sentinel Toolbox has an option to generate textures, and sometimes those can provide useful information to separate classes that might be very confusing. Regarding the ascending and descending difference in viewing angle, is it correct that they should be compared even with geometric correction? That is correct. Even with the geometric correction, they should not be compared. You can compare the product, but you should not mix them in the same analysis. Is it always recommended to do speckle filtering before terrain correction instead of speckle filtering as the last step? Yes, it's recommended. The last thing you want to do is terrain correction, because terrain correction is it's correcting the effects of the geometric effects, distortions of the terrain, and it is changing. It is doing some changes in the pixel values, and so yeah, you don't want to apply the speckle filter after it does this correction. You want to apply it before. Which band is good for water body extraction? HV is good for water body extraction. Talking about floods due to hurricanes, is it possible to monitor hurricanes with SAR? Which kind of approach is recommended? I'm thinking about this one. So SAR is normally not used to monitor hurricanes, but so SAR is an imaging radar, and there are scatterometers, which are non-imaging radars, and those are used to look at winds on the surface of the ocean, and look at wind and assess wind speeds, and wind directions, and so that is useful to monitor hurricanes per se, but not SAR. On what basis? And also SAR, remember, you don't have the temporal repeat really to do monitoring of hurricanes. On what basis should we adjust the histogram? On how things look, right? So you really want to adjust it so that you see the features, so that they're not washed out, so it's not too bright or it's not too dark. Can SAR be used to detect rain or snow inundation, or are the dielectric constant for ice and liquid water too similar? Actually, the dielectric constants for ice and liquid water are very different. So for ice, it's about 3. For liquid water, it's about 80. And so there are atmospheric radars that are used to detect rain, and they use much higher frequencies, so much shorter wavelengths so that they interact with the particles in the atmosphere. So radar is used to monitor rain. Oh, rain on snow inundation. Okay, rain on snow inundation. So I guess you're talking about snow that has puddles of rain over it. I'm not exactly sure. In that case, you'll detect a wet surface. Actually, if you have rain on snow, the snow is probably wet as well. So if the rain is puddled on the snow, then you'll be able to detect the open water and differentiate that from the snow surface. Is it better to stitch images over an area prior to analyzing them, or should they be analyzed separately? So if your images are from contiguous passes, you should mosaic them, right? If your images are from different dates, you should treat them differently. How to distinguish flooded versus non-flooded forested channels and urban areas? Okay, so I think this was explained in the presentation. In forested areas, whenever there's flooding, you have double bounds. in urban areas, you have double bounce regardless. So the same backscattering mechanism is found in urban areas. And so it's very difficult to distinguish, to separate flooded vegetation from urban areas. You can try some sort of like texture filter. What are the factors that affect the depth of L-band penetration through bare soil? The primary factor is the amount of water in the soil. That's by far the greatest factor. And so if you have a large amount of water, you're not going to penetrate almost at all, just maybe the top couple centimeters. If the soils are really dry, and there have been studies looking at penetration through really dry soils, then it can go down to a meter, even 2. Are we able to do classification using only one polarization? Yeah, great question. Actually, this was a question I couldn't get to last time. Yes, you can, and I have a lot of experience doing that. So you can use one polarization. You can apply texture filters. You can use like ancillary data sets, like a DEM, for example, and you can generate a classification. So with there's plenty of information in just one in just one polarization. If you take a look at one of the images, so let's just load this up. If you look at just one image, right? I mean, visually, there's a lot there in this image. There's a lot of variability. And so, yeah, you can classify just one image, whether it's HH or VV. So visually, you can just classify based on the different tones, from very light tones, medium, dark, super dark. Okay, and then and textures might help, as I mentioned, separate depending on what your sources of confusion are. Textures might be able to separate some of that confusion. In some research, thresholding dark pixels as water is used to distinguish flooded and non-flooded area. Can this approach still correct, given that flooded area appears white? Thresholding dark pixel as water is used to distinguish flooded and non-flooded area. Okay, I guess it depends on what you're talking when you say flooded, because with radar, there are two kind of flooding conditions. There's open water, which is a specular surface, and then there's flooded vegetation, which is a double bounce. And so, yes, you can use a threshold, definitely. In fact, if you take a look at these images, even just taking a look at the histogram, you can see how distinctive water is from everything else, right? And so, so easily you can just apply a threshold where everything above this value here, which would be 14 minus 14 dB, would be land, and everything below that is water. And the same thing for these inundated vegetation areas. They're just so much brighter than everything else that you can look at their values. By the way, if you go to pixel info and you pan around, you can see the values of at the pixel level. So let's just zoom in so you can see what I mean. And so if I pan around here, right, you're seeing the value up there. So we have a dB value in this area of -2. And if you pan around even like these brighter areas, it's much lower. So yeah, you can just set a threshold and say, all right, everything above -3 dB is flooded, you know, and you are going to get it confused with urban areas, and that's the issue. But yes, you can use thresholds. Okay, if you have no urban areas, then it's much easier. In some research, can we use KNN classifier for inundation mapping using Sentinel-1 data? Okay, that's a great question. And actually, that's a very relevant question because I read your mind and I knew that this question was going to be asked. And so what I did was I generated a classification using using the KNN classifier. And it's part of the options here. in the Sentinel toolbox. If you go to raster, classification, supervised, K and N. And so let me just load up. It turns out the results were quite similar to the ones from the previous, from the random forest. I tend to prefer the random forest one. It just picked up some subtleties that the KNN did not pick up. So I won't get to it, but this is the result from running the KNN classifier. And you can use the same images, the same stack, the same classes, and just run that. So what I suggest is explore the results that you can get with these different classifiers. Just compare it and determine which one gives you the best results. So that's not it. Here. Okay. In the classification exercise, there was clearly an impoundment, water behind the dam, yes. On the downstream side, there was a linear feature of very pixels. This appeared to be a channel. However, it was not clear whether this might be an overgrown stream or perhaps flowing water, or both. Is it possible to distinguish this? So let's go ahead and take a look at what you're talking about. So this is what you're talking about. And let me read the rest of your... Okay. There was a linear feature. This appeared to be a channel. So this channel here, the river, a small river, I'm wondering if that's what you're referring to. Okay, so what this is, that is actually specular reflection here, what you're seeing, because it's dark. So there is water running there through that channel. And let's see if we pick that up. Let's see. Okay, so if you're looking at the one here, we partly picked that up in some places. So I think that's what you're referring to. All right. We have gone through the process with ALOS pulsar and Sentinel-1 C-band. Is there an L-band for the same area from Sentinel or another radar image? That is the million-dollar question. You know, we've talked about all of these different options or parameters, radar parameters, and different wavelengths and polarizations, and it comes down to what data is available. And so really, the only data that's freely available right now, radar data, is Sentinel-1. So that's a C-band image, and it has it's been operational since 2014. ALOS pulsar is L-band, and there's data between 2006 and 2011, so they don't even overlap, unfortunately. But that's just what's available. So unfortunately, we have to kind of live with what's available. But it'll change. The future looks very bright in terms of radar. There are several sensors coming up in the next couple of years, which is very, very exciting. When would you use multi-look versus filter and deciding on the overall filter size? Okay. So multi-look is usually used when you have the SLC images. Those have radar amplitude and phase. But the Sentinel-1 toolbox also, with the Sentinel toolbox, you can apply a multi-look on the GRD image. And what it does is it takes your image and it resamples. So basically, it applies like an average filter, and then it resamples the image. So it lowers the size of the image. Um, and the overall filter size, that totally depends on your area, right? So if you have a lot of heterogeneity in your area, you really don't want to use a filter size that's too large, because you're going to lose that heterogeneity. It's going to be kind of average or lost in the large window. But if speckle is a big issue and your classification is just too speckly and too noisy, then you do want a larger filter. So there's always that trade-off, unfortunately. All right, you mentioned about texture of urban areas. How would you look at that? Okay. The way you look at that is you apply a texture filter. And the way you apply a texture filter is you go to raster, image analysis, texture analysis, gray level covariance. And you go to processing parameters, and here's a whole list of different textures. And these are especially helpful when you're using like one band. So texture, urban areas will be as bright as the flooded areas, as we just saw, I illustrated. And so some of these can have, some of these textures can have different values in flooded areas versus urban areas. And you need to experiment with that. But I found that there was one like entropy, for example, that helped when you had large urban areas and flooded vegetation around, that it really helped to separate those, to distinguish those two. Okay. What kind of polarization would be best for surface wash-off of soil close to the shorelines or river banks? Surface wash-off. I'm not sure what you mean by surface wash-off of soil. Like soil erosion? Maybe you can be a little more specific. Can SAR be used for extracting soil moisture? Can you recommend any trainings and RS other than SMAP? Okay, here's one thing for you guys to know. So there's SMAP out there, and SMAP is generating soil moisture products every 3 days on a global basis at 9-kilometer resolution. It uses a passive sensor called a radiometer that operates in a microwave frequency at L band, actually. Radar can be used for extracting soil moisture. The problem with radar is it's very complex. This is not really simple or straightforward to extract soil moisture using SAR. And the reason for that is, remember, you have a signal that's going through the medium. So if you have vegetation there, it's interacting with the vegetation. Part of that signal is reaching the soil. Then it's returning. Part of that signal, as it returns, it might have other interactions, and then it returns to the satellite. So that signal has a combination of many things, right? Part of it is you've got a component that's the vegetation, and you've got a component that's the soil. So basically, the way it works is you need to tease out the vegetation component to get to soil moisture. So it's not that straightforward. Dr. Heather McNairn, she's going to do an example of this in the next session. Okay, so the next one. How does one reduce scalloping effect in Sentinel-1 SLC? So I think this is in regards to an email that someone sent me about this, this banding effect. And, you know, it's very difficult to get rid of that banding effect. That banding effect is due to an error in the processing or some issue with the processing of the data. And so it's like the Landsat images that have this banding effect. It's just very hard to work with that. So I would suggest just using images that don't have that scalloping effect. Can you suggest a good reference text for SAR applications? There are a lot, and it is hard to know which is better. Okay, so this one is hard to answer because there's just so many applications. It's more, what would be helpful is if you have something in mind, like whatever your research is, you're looking at oil spills. Can SAR help me detect oil spills? Then I can tell you yes or no. But but just generally SAR applications, there are a lot. There are a lot. Can we measure snow water content from SAR data? Which bands are best and to which extent for snow monitoring, depth of penetration, etc.? Ooh, so snow water content, that's the holy grail. I think whoever can figure that out well will win the Nobel Prize, if there's ever a Nobel Prize in this area. So it's very tough, okay? There are many studies using SAR data to look at snow, especially when snow goes from a dry state to a wet state. And so with the shorter wavelengths, the ones that interact at the top of the surface, they're very sensitive to a change in dielectric in snow. So, for example, the beginning of the thaw up in the northern high latitudes when that snow starts to melt. There are, I think that there have been some publications looking at snow depth because of penetration. So if you look, you use different frequencies. Obviously, the longer frequency will penetrate deeper through the snow than the shorter frequency. So I think there have been studies using like K, U band, and L band to try to look at snow depth. And penetration is going to be limited by, obviously, how wet your snow is. So the wetter the snow, the less the penetration. We all know an urban area when we see it. When does urban change to non-urban for SAR purposes? How do we recognize that transition, say, in a visible image? That's a good question. That's a great question. I think it varies, but usually urban areas, yeah, there's a large urban areas, okay, so there's a lot of density in the middle. You've got a lot of buildings, you've got a lot of concrete, and then the further away you get from the middle, you start getting the surroundings, which are usually pasture lands or agricultural lands or more natural ecosystems. So it's that peri-urban area. So when does it change to non-urban? When you don't see that double bounce, that's when it changes. When you start seeing more of volume scattering. Is there a way to filter out Is there a way to filter out or correct for RFI interference prior to working with Sentinel-1 or other RadarSat data using the toolbox? So RFI interference, usually that's filtered out already. In most cases, it's not a big deal in dealing with these images. As far as I know, the Sentinel toolbox does not have an RFI filter. How will you do a multi-temporal flood detection over a rainy season? What kind of information do you receive? Google Earth has SAR GRD data. Have you played around with it? Okay, so how do you do a multi-temporal flood detection over a rainy season? So what you do is, especially with Sentinel, for example, you've got coverage every 6 days. So your area of interest, if you're looking at like length of inundation, say for a pixel, right? How long during a season, how long, every 2 weeks you're looking at the same pixel. Is it inundated? Is it not? And then you can determine how long that pixel remains inundated. I hope that answers your question. Google Earth has a SAR GRD data, so I have not played around with it, but I know that the Sentinel SAR data is in Google Earth Engine, and it's a great resource because you can do analysis on the cloud, and that's much easier than downloading the data. Which other early satellite images could be compared to Sentinel-1? Should one need to compare the changes in an area before 2014? So which other early satellite image could be compared to Sentinel-1? Right now, so let's see. There is not that much that's freely available that you can compare. the best thing that you have to compare is the ALOS pulsar. There was a satellite that flew in the 90s. It was a Japanese satellite. It was a precursor to ALOS pulsar, and that's called JRS-1. Okay, and that was an L-band SAR sensor. And the Alaska Satellite Facility has the data. However, it has a restricted access. So you need to basically submit a request for access of the data. And that satellite covered, let's see, it flew from, I think, around 1992 through 1998, around there. However, there was a project from that satellite called the Global Rainforest Mapping Project. And they created mosaics over major wetland regions around the world. And they created these mosaics for the wet season. They created one mosaic in the wet season and one mosaic in the dry season. And those mosaics are available. In fact, if you send me an email, I can point you to where you can access these mosaics. So if you're interested in South America, for example, the mosaic for the dry season was with images acquired during a 3-month period. I think it was in 1996. And the one for the wet season was around the same year with images acquired during a 3-month period during the wet season. Okay, so anything else? Okay, there's a question here. You mentioned about using ratios of 2 polarizations to reduce speckles on images. I think you misunderstood me because you do ratios to maximize your information, to really look at the unique information content in one image versus the other, but not to reduce speckle. Suspended sediments movement mapping. Is it possible from SAR? So remember, SAR is sensitive to structure and the dielectric properties of the surface, not to the chemical properties of the surface. So if you're looking at like suspended sediments, I guess that would translate into the color of the water. And that would be, optical would be more appropriate with that. Now, if the suspended sediments changes the roughness, so if there's an indirect link, if it changes the roughness of your water surface, then you might be able to tell the areas where you have suspended sediments versus areas where you don't. Where can I find data for Florida? The Sentinel, this Alaska Satellite Facility has global data. Okay, and thank you everyone for your kind comments. I think that's it for our session and the questions. Anything else, please just send me an email. I'm seeing a question here. I'll just get to this one last question. What is dB value range for soil, vegetation, crop, and water body? Wow, that's a really loaded question. And so it depends. If you're looking at it with VH or VV or HH or HV, actually HV and VH are going to be about the same. But generally, for vegetation, you're going to see dB values that are higher than for water bodies. Water bodies will be very low, as you've seen, around -20. It depends on the sensor, too, the noise level. For soils, if it's bare soils, it might be similar to water bodies, maybe a little higher, so it just depends. All right. So is that it for the questions? All right, thank you very much. Please tune in to the next webinar, again at the same time on Tuesday, August 14th. And remember, the last one will be Thursday, August 16th, and that one will be on interferometric SAR. The next one will be on crop mapping and characterizing soils. A great day or evening or morning, wherever you are in the world, and see you all soon. Bye-bye.